All right, welcome back. We are GAME3001 in the summer 2020 semester at George Brown, and it's week 10, part 1 of our broadcast. Today is the lecture part. We're going to do the lab portion at 3 p.m. today. That'll be live at 3. So for today, we're going to start with our lecture. So I wanted to start by talking about what's due. Remember that this Sunday, your assignment 3 is due. So that's kind of like part 1 of a 2-part assignment to create a short little game that has behavior, right? So you're giving your AI behavior, you're combining some of the learning that you went through in the first half of the semester with Alex, and you're putting it together in an assignment that culminates your learning, and it produces something interesting. It also, the hope is that some of the stuff we're talking about in AI, you're going to incorporate into your game project for game production. That's the hope, right? So that we can get you guys going with that. And also, since you're, again, the stuff that you're incorporating into your game production is something that you can carry forward into other semesters. So once you learn how to do stuff with AI, I mean, you can expand upon it. You can research, you can add more detail. So today we're going to be talking about state machines. We've talked about so far from a behavior perspective, this whole second half is all around behavior. So the last 3 weeks, the last 2 weeks, week 8 and 9, we've been basically talking about everything to do with behavior. So we talked about decision trees so far, we've talked about behavior trees, and this is the third talk about behavior, which is state machines. Now, typically what happens is you could bring state machines in at any time, but usually we talk about a decision tree first because they're a slightly simpler structure than a state machine. A state machine has transitions. A state machine can be more complex, but also a state machine is one of the most common constructs we're going to be talking about today. But before we get there, before we start off with state machines, what we're going to do first is I want to take a look at some code. So I have some an example of a project from last semester, last semester, and this is from a student, Herman Hum. He produced this project, assignment 3-4. Let's take a look and see what this is. So here's his project. You've got your character. You know, you're running around, and you've got a couple of different kinds of characters here, right? You've got a loadout that is I'm this guy here. You have a couple of characters that are a melee character, and of course I died because I'm not good at playing this game. He's got some, you know, you've got your character's health. Now he put his character's health on the bottom, so that's kind of something that he changed. He explained it as something that, as an example, was easier for him to implement. Notice how this one hid. This is your character that is a range character. He's hiding behind there, and he's going to come out and start firing back at the at my player character, right? So there you go. And if I don't finish them in time, they keep respawning. So that's what's going to happen every single time. There's a destructible environment, so if I go here, I can, you know, break these obstacles if I want to. This guy seems to like to hide, so I can try and kill him too. And when he goes to like half life, you know, he'll be actually going to thing. If I kill both of them, if I'm successful and I kill both of them, then I'm pretty good. But then if I don't, what'll end up happening is, if given enough time, what'll end up happening is that there'll be another loadout that comes through it if I can make it to that level, you know, which is kind of cool. All right. Yeah, I'm gonna die again. Anyways, but the point is, let me just show you one more thing before we go. One thing is you can always turn on a debug mode. You can see the nodes that are being used here. The nodes are in blue. Let's use our cover a little bit more. just not good today at playing this game. Normally I do better than how I'm doing right now. But let's chase this guy down. And almost had him. Oh yeah, here's the knight. Okay, so this guy, this character here is a much more difficult character to fight. He's more aggressive, and he's more difficult to fight. But notice that the nodes, there's not that many nodes. Like last week, what I talked about when we created our examples, we had a bunch of nodes. Here, Herman has only placed a few nodes, only the nodes he needs for traversal. And the reason for this is because as we, if I was to continue to put these nodes in play, right, as an example, and then what would happen is the characters would transition into nodes that they can go to, right? And it's easier for a line of sight perspective, as an example, if there's less nodes, and from a performance perspective too, right? Because otherwise, what's going to happen is you're going to get to, damn, it's really quite difficult. It's going to get to the point where it gets bogged down, right? So again, there's 3 enemies that have been built in here, which is kind of cool. And you can see how the enemies keep their distance and run away and kind of go through all those behaviors that we talked about before. All right, so really complex, but I mean, this is an example of a project that has really, really good marks. He got an A+ on this one. A couple things that he did. He used a tile map to make the map interesting. So he overlaid it obviously on top of the nodes. You can see that the nodes can turn on and off. This is kind of a debug mode that he's put together. Again, you can see the different nodes. And you can see that there's other kind of nodes. These blue nodes are nodes that can be used from to kind of indicate line of sight. So these nodes here are travel nodes, as an example, and these blue nodes are nodes around each of the obstacles. So there's several different kinds of nodes. So that way it can help the AI do things like perform their behavior, like hide behind an obstacle and so on. So we're going to talk about more about that during our lab, but I wanted to share that with you. So questions are on that. So take a look at that, and that's the kind of stuff that that can be done given enough time and attention. I think that's a good example of what you can come up with. Now he did it alone. He didn't work with anybody else. So and Herman is someone who's really works hard. He spent many hours. He says he spent more than 50 hours on this assignment combined. So it's assignment 3 and 4. And I think he's got good results as an outcome, right? So. Do I expect you to spend 50 hours on this assignment? Well, no, but remember that each assignment, assignment 3 is worth 10% and assignment 4 is worth 15%, which works out to be like 25% of your grade, if I'm not wrong. And so 25% of your grade is pretty hefty. That means you should spend at least 25 hours combined with your partner in that range. That's the expectation. So hopefully by this weekend, you're going to have your base happening. So that'll be assignment 3, where you'll have your base enemy, you'll have line of sight, things that I've already given you, plus things that you're going to add in. I recommend having the nice map and everything else ready to go this time around. So then when it comes to assignment 4, it'll be easier for you to put things together. Also, one thing I'm going to do during lab today is I'm going to talk about before we start recording. I'm going to ask everybody what their groups are. I think it's important to understand who you're grouped with. Do you have a group member? All that kind of stuff. Do you plan on doing this thing on your own? I'll ask all those kind of questions during lab. Okay, so that's kind of something I wanted to share with you before we move on. So again, any questions, comments about that game? Again, it's a project that he put together only for assignment 3 and 4 for last semester. Okay, no comments. Yeah, I thought it was really good too. I think that his the comment was it's good AI. Yeah, I mean, he's used some really cool things, and we'll talk about some of the technology that he put together during lab. I'll show you some of this code and so on, so you get a sense of how he built it out and what he did. I asked Herman about sharing his project with everyone, and he said it was okay. So hopefully that'll be good. It'll be a good case study. Here's an example, and let's take a look at some of the ways he did it, kind of stuff. Okay, so today now let's go into the meat of what we're talking about today. So we're into state machines. So what are they? And you might have heard about state machines already. Some people confuse them with what they are, but let's suppose, again, we're talking about behavior, and you have a simple action. As an example here, we have a Covenant Warrior in Halo, and they'll stand at their post until they notice line of sight or some kind of detection. It could be a radius that the player is inside the inside range or whatever, and then they'll switch into attack mode. So just like we've talked about before, you have a condition, and that condition triggers the state change in some ways. Okay, so we're going to start talking about state a little bit. So again, we've talked about decision trees as well as behavior trees in order for us to implement decision making. And this time we're going to be talking about state machines and how they're unique and different than decision trees. Okay, so it's one of the most common techniques for decision making, and the reason for it is because it's again a very simple implementation. I think they're easier than behavior trees. Behavior trees are more complex, but then again, we're talking about, like last week when we talked about behavior trees, we talked about sequences. If I have to do a sequence of actions, then I would use something more of a behavior tree. If I'm just going to move my autonomous character AI from one state into another state, let's say for example I move from a transition from, let's say, a patrol state into an attack state, and that's all I'm doing, sometimes that's easier to do with a decision tree or a state machine as opposed to a behavior tree. A behavior tree is more when I have a complex set of behaviors that I want to accomplish. And you can combine all the three things that we've talked about so far. We can combine decision trees and state machines and behavior trees in order for you to have more complex AI. But there's two things that we want to talk about. There is, for states in general, we want to talk about the world. So that is part of the state. So when I say, if I talk about the character state, the state that the character's in, and I don't want to use state too much, but think about this as almost like a set of conditions that exists for the world. So when the character's in a particular state, we look at the world as well. Where is he, or where is the character in the world? Is the character in a specific position? Is the character in danger or not? That kind of thing. So that is what we look at when we look at state. And then we also look at internal state. So there's external state and internal state again. External state, state of the world. Internal state is like, okay, what's the character like? What is the character's health? How powerful is the character? Does the character have ammo? Does the character need to eat? As an example, what is the internal character makeup, right? So both of those two things combined, external and internal, make up the state of your character, your autonomous character. And then when all those factors are in play, we can make a decision based on all of those conditions combined. That is the way we do state machines. And by the way, this can work great for board games. And a good example of this is something like if I'm playing Monopoly, as an example. When we talk about Monopoly, a board game, and I'm just giving an example, and let's pull up Monopoly just to talk about something a little bit more complex than what we're used to. So if I just pull up Monopoly here, not online, let's just get an image of Monopoly. Here's an image of Monopoly. So you can see this is Hasbro, of course, and Monopoly has a very simple, it's a very simple board game. We have multiple players, a multiplayer game, right? As an example, and everyone starts at the go square. In the initial state of all the characters are all in the same position. No one has any properties, as an example, and everyone has the exact same amount of money. So we can say that everyone is in the initial state. So in Monopoly, right? Then we roll off, and whoever goes first, whoever gets the highest roll, this is how it's normally played in most these types of games, especially, this one. Whoever goes first, whoever rolls off, then the highest roll wins. They go first. They make a roll, and then they take their turn. Now this is a turn-based game. It's not a real-time game, but it doesn't matter. So let's say, for example, I roll a 7, or here the 7's been rolled. So I go 1, 2, 3, 4, 5, 6, 7. I'm on chance. Okay, so now the first character that's rolled, the state for them is different now than the state for all the other characters, because when we've moved externally, we're in a different position from a game world perspective. We're in the chance on the chance square. That's number one. Next thing is, because I'm on the chance square, I've triggered a condition. I have to pick up the chance card, right, as an example. So I pick up the chance card and read that chance card, and whatever the chance card tells me to do, that is what is going to influence my next set of actions. Okay? And then as the gameplay progresses, if I accumulate properties, if I have less money, if I'm in a different position, if characters create things like houses and hotels on their properties, if they own multiple properties of the same color, and so on, it changes the entire state of the world, and as a result, the state of play. Okay. Now I'm using this as an example, board game state, but the idea is the same when it comes to state, when it comes to our games, right? We have a state. Think about Herman's game that we just saw, right? Herman's character starts off, there's 3 enemies that come into play at the same time. Depending on where each of the enemies are, the game state is going to be slightly different. Now here, Herman doesn't really care about that stuff when he made his game. He's just following my assignments, right? But imagine a character now, it's got to make a decision, and it's going to be based on the state of the world, right? So where am I? What's my health? Who's around me? Do I have help or not? Am I autonomous? I work on my own, or do I have friends? Is the AI collaborating with other AIs in order for them to defeat the player, right? So these all can be factors in making decisions, and we can call these states. Okay, so when I say state in your mind, and even on the final test that you're going to have, right? Remember that state doesn't mean moving from patrol state necessarily into attack state, all right? It's what's the external state, what's the internal state, right? And then what is the trigger that's going to move me from one state into the other, or transition me from one state to the other, right? So again, in most state machines, if I talk about a basic state machine, character is in a single state at one time. Okay, so they can't occupy more than one state in a simple state machine. Okay, so they're in one state, and as long as they're in the same state, they're going to keep carrying out the same action. So that means that if I'm in a patrol state, I'm always going to be just patrolling, as an example. I'm going to keep moving around the board. And then each of the states is going to be other kinds of states I can be in. I can be kind of drawn together by a set of transition lines. Think about these as a directed line that goes from one state to the other state. One thing that I can't do is I can't move into a state that I don't have a connection with. All right, that's one thing to note. So I can't go from, let's say, patrol state into an attack state if I don't have that particular transition. All right, maybe I have to go from patrol state. I got to do something else first before I go into attack state, as an example. Let's say I have to, go into ready state or attack ready state before I go into attack state. I can't directly go into attack state. I got to get my weapons ready, because maybe in patrol state I don't have my weapons out. Maybe I have a torch or something else when I'm walking around a dungeon. Let's say if I'm an autonomous character, right? So I may have to transition from one state to the other. And a transition is basically, it's a line of action that goes from the current state to the target state. And it's associated with some kind of condition that's going to trigger my transition, right? When the transition is triggered, we say it's fired. It has fired finally, right? So something that triggers a transition is some kind of condition. Transition, condition, I know the word is kind of the same. But a condition is like something happened, an event that occurred that triggers the change. That's what it is, from one state to the other. And when it's triggered, we can say that transition's fired. Okay? So then, if I was going to wrap this up at a very high level from a basic state machine, a state machine consists of these 4 components: states, transitions, conditions, and events. All right? These are the 4 things that you would need in a state machine. Of course, under the states, you'd also have, it would define some kind of behavior that produces some actions. Okay, that's important too. And then the other thing is that a state machine also must have some kind of initial state which provides a starting point. Think about this as the entry point into the entire behavior. And we also define a current state, something that the autonomous character is currently doing, some action that they're continuously doing because of the state that they're in. Okay. So let's think about a simple state machine like being on guard as an example. So we're on guard. We have a trigger. So notice that there's an arrow. First of all, this right here is, you've got the circle and the arrow. Circle, arrow, and this is a UML diagram, right? The circle says this is the entry point. So we start here, and I'm on guard. I don't have any transition condition right here, right? There's no condition. I just start here and I'm immediately on guard. That's the starting state, the initial state. Okay, notice that there are 2 options for being on guard. I can transition from being on guard to running away, or from being on guard to fighting. Okay, why? Because there's 2 arrows here. You can see that there are 2 arrows. Okay, notice that there is no transition from running away back to fighting. I can't go to the fighting state when I'm running away. There is no transition to do that, the way I've defined this simple state machine as an example. The condition that triggers the transition between being on guard and fighting is seeing the enemy. Okay? The condition that triggers being on guard to running away is seeing a big enemy. A big enemy and a small enemy. Big enemy would be a more powerful enemy than the guard. Seeing a small enemy is a less powerful enemy than the guard. Now this is the transition happens, or the condition can be triggered. You can trigger the transition if somehow the guard can tell what a small enemy is and a big enemy is. Maybe the small enemy will be physically small, like let's say in a fantasy type role-playing game, a small enemy could be something like a halfling, and a big enemy could be something like an ogre, right? You can also think about this in a military style game as a small enemy being a small group of attackers, when a large enemy could be a large group of attackers with many guns, as an example. So these are the conditions that trigger the transition from one state to the other state. If I'm losing the fight, that can also trigger the condition, or a condition that triggers the transition between fighting and running away. Okay, so there's 2 ways to get to the running away state. Okay. Notice that there's only one way to get back to the guard state in this little transition and this little state machine. You can't get there from fighting, right? You have to go through running away, and then when you've escaped, you can get back to fighting, to being on guard. So it's like, what if? Here's something. What if when I fight the enemy, I defeat them? What happens then? This is not defined in this state. Okay, I'm just saying. Maybe you'd want to have a more complex state machine where it says, okay, defeated the enemy, then, hey, let's go back to be on guard again. The other thing we can look at, which is very common as well, is a state machine for Pac-Man. All right, that's a very common state machine as well that we would have seen as well. So if I was to see a state machine for Pac-Man, that's a very common example out there. So here is a potential state machine for Pac-Man. Start. So there's the start. I wander the maze. As an example, I have some kind of transition, a condition that triggers the transition from wandering the maze to chasing Pac-Man. This is the ghost, obviously, that we're looking at here, right? The ghost AI, right? So we spot Pac-Man. Cool. So then we chase Pac-Man. Okay, cool. So now, from chasing Pac-Man, there's only one line of egress from chasing Pac-Man to fleeing from Pac-Man, right? If Pac-Man eats a pellet, right? The other way is, what happens if I go back? If I lose Pac-Man, I go back to here, right? So there's some stuff that happens. One thing that's missing in here is what happens if you actually catch Pac-Man, right? There's no state in here that talks about that. So again, there's other ones. It might be a good exercise for you guys to look at other things like that. Here's another one. I'm in the ghost base. That's my current state. As an example, you can see this is a double circle they've used here. We leave the base. We chase Pac-Man. If Pac-Man eats a power pill, then we leave. We kind of flee. As an example. But that's interesting. I'm chasing him, and then he's eating a power pill. Well, what about if I eat Pac-Man, or there is nothing like that here? And you can see some other examples of that as well. So state machines are kind of interesting. There's other, integrations like this, or under other examples of Pac-Man, but Pac-Man's a very popular one to take a look at for this one. So this is, again, a very simple state machine. So again, we talked about the Unified Modeling Language, UML, which is basically the way we're drawing this. So if I ever get you guys to draw a diagram, or if you ever see a diagram on a test, then states are shown as curved corner boxes, so like this typically. And in this course, that's what they're like. Transitions are arrowed lines, so some kind of arrow. Condition are in square brackets, so square brackets. All right, that's how it's like. And then a solid circle has only one transition, and it signifies the initial state. Okay, so it's very similar. A decision tree could have this, the same set of decisions is always used, and any action that can be reached in the decision tree can be reached by basically going through the decision tree, right? That's one thing that can happen. So any actions available from that decision tree at the beginning of the state, okay? Whereas in state machines, not every action is always available. It really depends on where you start and what triggers the transition change from one state to the next. So a state machine is different than a decision tree. One thing we can do is we can convert a decision tree into a state machine, but you can't convert a state machine easily into a decision tree. It's more difficult to go backwards the other way. Okay? So one thing to note. We also talk about in Game AI something called a finite state machine, right? And this is what we're talking about here. We're saying that there's a finite or limited set of options that an AI can take based on the conditions and the transitions that have been implemented or coded, right? And sometimes what happens is people in computer science, they also have something called a finite state machine as an example, and usually it has to do with something simple. For example, we might think about a finite state machine in computer science as parsing some kind of text, or maybe even something that looks like a simple switch case statement. And a good example of this is when we're moving from one state to another in our game when a player dies. All right, so for example, I'm in the start state, I press the button, I'm waiting for the button to be pressed. When the button is pressed, I move into my play state, right? From my play state, as an example, I'm fighting, and then if the player dies, they go into the end state, right? Now notice it's very simple, right? But this is more like the computer science finite state machine, as opposed to the state machine that we're talking about, which is we're looking at the state of the world, the external state, and we look at the internal state of an autonomous character. Now we're making a decision based on those two things. How are those two? How is that condition, the condition of the world and the condition of the internal condition of the player? How is that going to influence the player's decision making? That's a different question than, I'm pressing the button, I'm going to my play state, and then from there, if I die, I go to my end state. That's very simple. Okay, that's not what we're talking about. It's not the same thing, although they're called the same things from a computer science perspective. So when we talk about game finite state machine, which is different than the computer science finite state machine in some ways, right? More or less what we're talking about is we have this class base, the one they propose in the book, and there's different ways of implementing a finite state machine, and there's no quote unquote correct way, right? As an example, there's tons of different ways to do it. Then in the book, what they start talking about is the problem that they want to solve. So here's what the problem they want to solve. They say, and this is the author. The author basically says we would like to create a general system that supports arbitrary state machines with any kind of transition condition. All right, and the state machine will conform to the structure given above. So things like I can move from one transition to the other, or one state to the other, given a condition that's going to trigger a transition, right? That's what's going to happen, and I can move only to other states that are connected with the current state that I'm in. Okay, I can't move to a state that's not connected, or there's no neighbors, as an example of another kind of state. I can't just jump to a state randomly just because I fulfill a condition of that state. I have to actually have a line or some kind of connection with it. So when it comes to the algorithm, we're going to be talking about the same thing. I'm just going to go into it right now. One thing that they have is an update, and the update gets checked every frame, right? So again, we have something called an initial state, right, which is of type state, and we're going to get into this more in the lab portion, but I want to just talk about it a little bit because this is the kind of the base algorithm for the entire state machine. Notice that there is a state class, and the state class, I'm just going to go in there for a second. It looks like this. The state class can do a couple things. It can get actions, get entry actions, get exit actions, get transitions, all those things. And if you notice there, it returns, the arrow here in pseudocode means returns. It returns an action array. It returns an action array. So these three things, exit actions, and so on, all the actions returns an action array, and the transitions returns a transition array, right? So it could be more than one type of transition that needs to happen, or transition group. Okay, that's what state is. So if we go back here, here we're using composition. So state machine doesn't inherit from any other class, all right? It's a base class, and we're only in one state at a time. We have an initial state, which is some state that has what we talked about before, and we have our current state, and the initial state and the current state could be totally different. All right, when we first start off, when it's initialized, the current state is the initial state. Okay, that's the way it works. Okay, but we still keep track of the initial state, and the reason for this is because we can always, if I go back and restart the behavior again, I want to know where to start. So initial state is basically the entry point for my behavior. That's what it is. Similar to a decision tree, where the top of the decision tree is the root node, the initial state would be the root of all behavior for the state machine. Okay, that's the initial state. So again, I always think about this as like the start state. I'm in patrol state. If I first see an enemy, the enemy might be in patrol state, and that's their initial state. So on update, this update function, what it does is it returns an action every frame. Okay, so again, we kind of look and see if the state has been triggered, right? And triggered is a transition, the transition that's been triggered. We start off with null, so no transition has been triggered. That's what happens initially. And then for every transition in the current state, we want to get the get transitions. Okay, so this is for every transition and all the possible transitions. That's what this means here. If the transition is triggered, then triggered is equal to the transition that we're looking at. So triggered is the new state. Okay, and then we're going to break out of this for loop. We're going to stop the for loop if we find a transition that's triggered. Okay, and then if the transition is triggered, then we want to do is we want to find the target state. So the target state is, we take a look at the transition that's been triggered. Remember, triggered is just a transition. And we get the target state based on what's the next state that that transition has, as an example. Okay, I know this is kind of hard to read because we're looking at pseudocode, but bear with me for a second while we go through this one example. All right. And then if it's triggered, the actions we're going to take, there might be a group of actions that we have to take. We look at the current state and we look at exit actions. What do I do when I'm exiting this state? For example, maybe what I'm going to do is if I'm moving from patrol state into a fight state, maybe I have to pull up my weapons. That could be an exit action, right? If I'm moving from one state to the other state. And then if I'm moving to fight state from patrol state. The other thing is, I also want to add other actions that I want to make. For example, maybe I want to have other kinds of actions. Let's say I'm pulling up my weapons. That's one action, and the next action might be I want to when I'm going to fight, I need to move into position. That might be another action. I have to do an animation or something like that, and I'm moving into position, right? And then the next one might be something another action we could add. And remember, actions is an action array. These are all things that are going to be performed at once. We're kind of building up a group of things that are going to be done, right? These are all the actions, and then maybe there's some kind of entry action. So when I approach the player character, if I'm the autonomous AI, right, what are the entry actions? Maybe what I need to do is there might be some kind of sound, or I might have to, again, when I'm near enough, I have to slow my character down. Those are entry actions, right? And then once the transition is complete, then the current state is now into the target state. So I've done all these things. I've taken all the actions that I need to take. I know I've built up a list of actions that I've got to take, and the transition then is complete. And then what I do is I return the actions. I return all the actions that need to be done if the state has been triggered, the new state has been triggered. Else, if I haven't triggered anything, and this is all in the update function, then I return the current state actions. So I keep doing what I've been doing the whole time. If I haven't triggered something new, then maybe I just keep patrolling, because that's the only thing that is part of those set of actions for the state, right? Patrol action, So that is the basic state machine. So again, if you think about this, if I go back to that basic diagram again, right? If I'm on guard and I get all possible actions, these are all possible different states, from this particular state, right? These are all different possible states. Something is going to trigger me to go from either fight or to run away. Those are the two options that I have. I can't do any other things. And that's really listed right here in the pseudocode, right? So again, it tells you that for every transition, I have more than one transition, right, that I can go to, right? How many transitions do I have here? I have 2 possible transitions. These are the arrows that I can go to here, 2 transitions. So I get for each transition, I go through and I look at the condition, and for these transitions, are the conditions met? If the condition's met to see the small enemy, right, then I go fight. If the condition is met to see the big enemy, then I run away. Those are the 2 options that I have for these 2 transitions. Okay, pretty straightforward. And we talked about the state class, and the state class has all these different kinds of things: entry actions, exit actions, transitions, and a group of actions that are associated with the state itself. Okay. For example, fighting. If I'm in melee combat, maybe that could be another kind of state machine, right? Another state which is melee combat, right? Or maybe another state could be range combat, right? So there's 2 different states, right? Depending on how the state machine is created, I could say that, well, if I'm within this range, so a condition, I trigger my transition to start, using range combat, right? But if the player character comes too close, I move from doing range combat to melee combat, because that's maybe a better choice of action. Because maybe I would get some kind of minuses. I would lose a buff, let's say, for example, if the character is in melee range and I'm trying to do a ranged attack, right? Maybe the player is going to have an advantage, and maybe the AI doesn't want that, so they're going to shift weapons. I'm going to change from my bow to my sword, as an example. And that could be one of the entry actions that I'm doing from going from, let's say, a ranged attack to a melee attack, right? So I'm moving from bow to a sword, right? And what happens when I do, what exit actions do I take when I move, if any? Like, I may not have exit actions, but maybe there's some kind of, as an example, I could have when I'm moving from a bow to a sword, maybe there could be some kind of new animation that I have to make, as an example, right? Or some kind of sound. There could be an exit action that you're too close, okay, I'm going to switch my sword now, kind of thing. And then the action would be, okay, now start fighting, start doing your melee attack with all that entails. Okay, so that could be, then this is what the states would, each state would have these different kinds of conditions. So the transition then, if I was going to look at the transition, transitions would have, is the transition triggered? It's a Boolean. What's the target state? If the transition is triggered, then I go to the target state. And then I would have actions for the transition itself, right? So there'd be a group of actions that I build up that I have an action array that I build up as I'm transitioning. That's what I'm doing. Okay, so hopefully that was clear. Again, what we're trying to do is describe how the state machine would work, right? And it talks about here how exactly what I kind of talked about with transition implementation. How do I do that? A lot of times, one thing to keep in mind is state machines are often defined in a data file, all right, and we read it at runtime. Why? Because if I define a some kind of data, let's say in JSON format, right, or even in XML, and I put together a set of transitions and states and how they're connected. Again, you could organize this data format to describe the diagram we were just talking about. Then what we can do is we can load up each of the behavior state machines at runtime. So let's say if I wanted to tweak something, as an example, what I want to do is build up that state machine, and maybe I can modify the AI if I notice that it needs a bit of a tweak, if I want to make another kind of transition, right? So I could, again, I can hold that stuff on a data file, and then it wouldn't be so much hard-coded. I can adjust it. Also, the other thing that you can think about this is this. Imagine if the data file can be overwritten. I can have a temporary data file. I can read in the data file in memory, and then what I can do is that if the autonomous character can learn, right? And somehow, kind of save out its own data file, based on the state of the world, right? So now I've learned, the character does these 5 things. Well, then, what? I'm going to add, this is the most common behavior the player takes. I'm going to, to do this kind of stuff. But learning is something we're going to cover in a later lesson. But I'm saying, think about that. I can have my state machine, or even my decision tree outlined in a data file, as opposed for it to be hard-coded. We're going to talk about hard-coding it in a second. So again, when it comes to combining tests, so let's say, for example, I want to have multiple conditions at the same time, like let's say an AND condition. Example, the enemy is far away and the health is low, as an example. That can combine to trigger some kind of transition, right? And in decision trees, it's a little bit easier to make, but from a state machine perspective, it's a little bit more challenging to do, especially when you're doing something that's polymorphic, right? So that's kind of a challenge. So what you can do instead is you have a some kind of, here's your class transition, and you have a set of actions, right? And then your target state, and you get the target state. You can do that, which returns the targets. These are all, this is just the class transition and how it's been defined. Again, one thing that we can do with a transition, a condition, here's the condition now. It's usually done in a test. So I want to check to see if a condition has been met. We have some kind of test method that tests to see if the condition has been met. And if it has, then we message the transition that the condition's been met for it to transition to the next state. That's how it works. And you can have different kinds of condition. Here we have a float condition that extends the condition superclass. This is the condition superclass, which just has a test. And you can, most likely this test method is going to be pure virtual again. And we're going to define it or implement the test method here inside of a specific type of condition, a float condition, right, as an example, where we look at minimum and maximum values. Okay? And there's different kinds of other conditions, an and condition, a not condition, an or condition. We have to specify these, and we can combine conditions. Condition A and condition B could be something that we give to an and condition. If both those conditions are met, if, example, condition A and condition B, then the test returns true. If the not condition is met, that means if the not condition is not met, then it's met. If it's met, then it's not met. All right, so that returns the test condition with whatever that is, and then the or condition is either condition A or condition B is met, and then it returns true. So that's how you can do it when it comes to conditions. So that's pretty good. I mean, again, it's not terribly sophisticated. It's just kind of similar to what we did with decision trees. So a couple weaknesses. Lots of method calls, lots and lots of methods and methods. Almost like sometimes when I think about finite state machines, I'm thinking there's like method hell. It's like going from one method to the other. We're calling tons of methods on the stack, and each of the methods has to resolve. For example, I'm calling, hey, let's do all these transitions. Okay, fine. After these transitions are done, let's get into the next state. Cool. Okay, and every frame this is happening during update. One thing also to note is just like the same as what we talked about for behavior trees and decision trees, you want to delay, you want to implement delay a lot of times when it comes to some of this stuff, because if you automatically transition to some other state every frame, there's going to be some jitter when it comes to the final implementation, which is what we don't want. Let's talk about hard-coded FSM. Hard-coded finite state machines is like probably still the most common approach. I would say less common than before. Now that game engines are more flexible. For example, if you're making a generic, if you're using a generic, game engine like let's say Unity or Unreal, then it'd be less common. But if you're making your own homegrown engine and you're not going to make it for any other game but one game that you're making, then hard coding it might be okay, because you're only going to have one set of actions that your enemies are ever going to have, right? You're not going to, if you're not extending it, or if you're not making a game engine, right? You're just making a game engine for your game. You're not making a generic game engine. Then hard coding your finite state machine might be okay. It might be a good way of doing things. Now there's disadvantages and advantages to this. Let's talk about those things. So the one way to do it would have some kind of enumerated value, as an example, indicating which state is currently occupied, and then a function that checks if a transition should be followed. So here's an example of that, which is very similar to what we talked about earlier with the common computer science finite state machine. So here's my finite state machine. Maybe I would have the enumeration in a separate file. It doesn't matter, but it's usually part of the class. So example, we have a finite state, which is patrol, defend, or sleep, right? And then my state, which is some kind of state. We might have an initial state as an example that we set up. Maybe the initial state is patrol. Okay. And then on update, every update, if my state is patrol, and this could be a switch case as opposed to if else. Switch case works really great for this kind of thing, especially with when it comes to enumerations, right? Case, patrol, then I can ask some questions. Here are the triggers for the transitions. Can I see the player? Yes. Then defend, right? Else I can't see the player. You know what? Maybe then I'm going to shift to sleep. So I'm not sleep. I'm just sleeping for a while. All right. Sleep might be pause and wait, as an example. So maybe the sleep the sleep state might be like, pause where you are for 4 frames or 5 frames or whatever it's going to be, right? Or pause for this frame, as an example. Keep pausing for this frame, right? Else, let's say case 2, let's say if I'm in defend mode, then if I can't see the player, I go back to patrol. I switch back to patrol, okay? And if I'm in sleep mode, and if I'm not tired, then I keep patrolling. If I'm tired though, maybe I stay in sleep mode, right? I stay in sleep mode if I'm still tired. And maybe what happens is tired and not tired. The way that happens would be if I was to, and also there's a couple of things we can see here, a couple of methods that we're checking. Conditions, tired and can see player. Those are conditions that are gonna make the transition happen. Okay. Here's another one. Function, notify noise heard, right? If my state is sleep and volume is greater than 10, so maybe somehow the AI has heard noise somehow, or in this case it might be something like you're walking, you have a some kind of sensing radius where this person is sleeping. The AI has sensing radius, and every time you walk it generates, if you're far enough away, maybe it only generates a volume of 3 far enough away. But as you come closer, maybe there's a point where you're generating a volume that's higher than 3, let's say higher than 10, as soon as that person wakes up and starts to defend, right? Or maybe it's based on a level of challenge. For example, maybe you're trying to creep or sneak, and sneaking only makes a volume of, let's say, 5 minus your sneak level, right? So if you can have a level in the game between 1 and 5, and if your sneak level is 5 and you're sneaking around, maybe then your total volume would be 0, so you're not making any noise, right? You can go right up to the player or the character and you're not gonna make noise. But if you're not sneaking, as an example, and you then maybe what it is you get a volume, a regular volume, whatever that would be, based on the distance, right? So I mean, again, there's different ways of triggering this thing, but this is an example of a hard-coded finite state machine where there's only a few actions that this particular character can take, and every character would have their own little finite state machine that they would follow. Okay. Is this bad for assignment 3 and 4? The answer is no. If you wanted to use a finite state machine, remember there's 3 things you can use for assignment 3 and 4. One is decision tree. The second one is a behavior tree, and the third one would be a finite state machine. Any one of those types of decision techniques is okay, and if you hard-coded any of them, it's okay. I don't expect you guys to make a generic finite state machine decision tree or a behavior tree so that you can use it as an example in other games. It can just be specifically for your game, so it could be partially hard-coded. That's okay. And so here we have a get action, where we could have an action block which allows us to say if my state is equal patrol, then return a new patrol action. If my state is defend, then return a new defend action. And if my state is sleep, then return some kind of sleep action. Okay, so this could be the action that you get, the get action from each of the states. So weaknesses, easy to write is great, but difficult to maintain, right? Because we think about this now again. If I want to make a change in the first way, I have a file, I make changes to the file. It's not hard-coded. It can just, my finite state machine system is going to read the file and then create my behavior set, as an example, for the enemy based on what I've read from the file. And if the file changes, I'm going to change my behavior. And you can, again, in the file, what you would do is you would indicate transitions, And the transitions, anything that you indicate in the file, by the way, has to exist in code, right? Sometimes it's not written in a file. Sometimes we use a scripting language, a higher level scripting language like Lua as a good example. Lua is a very popular higher level scripting language to use with homegrown engines. And what you do is you write it in a little script, and the little script itself is, you write actually a loader that loads the script, parses it, and then creates the finite state machine after the script has been loaded and run. Okay, so it's lots of ways to do this thing. But the advantages of the hard-coded finite state machine, although easy to write, is there's also disadvantages because of the maintenance. And especially since if we get a very much more complex behavior, then hard-coded finite state machine doesn't make any sense. It's really difficult to put into place, right? And the other thing is, once we start getting into more complex finite state machines, for example, a hierarchical finite state machine, it's really difficult to put together. As an example, if it's not as flexible. If you have the flexible implementation from the first example, then it's easier at the end. You pay up front. Flexible implementation is more difficult to write because it requires more generics, it requires more planning, and so on. But you pay up front for better usability later. All right, that's the advantage. So again, sometimes what can happen is for simple finite state machines, as an example, it's okay to write the things that we've written so far for a simple finite state machine, right? But sometimes you have things like alarm behaviors, and these alarm behaviors can trigger other finite state machines to come into play. So here's an example. We can look at a robot, right? The robot is, and the example might be a service robot that moves around a facility cleaning the floors, right? It has a state machine to do this. And it might search around for objects that have been dropped, pick one up when it finds it, and carry it off to the trash, right? But sometimes what can happen is that the robot also has to charge, right? And if it runs out of charge, then maybe it's not going to be able to do what it's supposed to do. So again, you can see the entry point. We're searching for trash. If I see trash, then I head for the trash, right? As an example, the transition is I got the item. Maybe they get the item, as an example. I saw the item. So here, as I seen the item, I go pick up the item. I got the item. I head to the compactor. When I head to the compactor, I dispose of the item. When the item is disposed, I go back to searching. Very simple state machine. All right, so this is okay, right? But what happens when there is another condition? For example, I'm running low on power and I have to charge. Which one is priority? Do I prioritize picking up the trash, or do I prioritize, as an example, recharging? Which one is it? And it really depends on how you code your state machine. Okay? So sometimes what it requires, because of difficulty, and it might look like something like this, it could be more complex. So the same state machine might have a bunch of times we have to check to see if we have power. So an example would be, hey, here's my state machine. I'm seeing the trash, heading for the trash, picking it up, putting it into the compactor. But what if I search for the trash, right? I have no power, or my power is low, is what the right thing would do. I'm going to go get power. All right, go get power. I go into the charging station. When I'm recharged, I go back to the last state that I was in. So search. Same thing for heading for trash. Same thing for heading to the compactor. I might have the item here. I have the item, but I'm going to head to the compactor. But before I do that, I have to charge up, as an example. And then I can do everything. And then finally, I can go back to searching again. So this can create many more transitions. So going from 1, 2, 3 transitions, now I have 1, 2, 3, 4, 5, 6, 7, 8, 9 transitions. So I've tripled the amount of transitions that I have, which triples the amount of conditions, right? I've tripled the amount of conditions that I'm looking at, as an example, because I'm in search and I have to check to see if I'm recharged or not, or at least doubles. Let's say I double the amount of of conditions and transitions that I have, which can be really challenging to do. This is an inefficient way of doing things, right? So what's better, instead of doing it this way, right, if I have something else I have to check at the same time that could interrupt my journey, picking up trash as a robot, right? I'm just going to skip down to this part. It might be best if we kind of put things into this and these two hierarchical states. So again, here we've refactored, if you think about this. We have a cleanup state. Here's my cleanup state. Or I go to the get power state. Which state am I in? Am I cleaning up or am I getting power? If I'm in cleanup state, then I go through and do what I'm doing. If I need to get power at any time, it will check, the cleanup state will check to see if I have power, right? And if I need to be recharged, I'm going to go get recharged. It could be at any point inside the state that I'm checking to see if I get power. So this is the same thing that we've written before, but we're only going to check one time, because this state here, the cleanup state, is inside of this higher level state. The higher level state, which has get power and clean up, that's the outer level. And here we can say that this one here, this getting trash and picking up trash, is the inner level, or a nested state, right? So, I mean, at the at the beginning, this is just, it's almost like a state machine inside of a state machine. That's why it's hierarchical. One state is on the outside that controls the priorities, cleaning up or getting power, and the inside states, you could have another inside state for a get power. You don't know, it's like a black box that's in here. That, kind of, maybe there's something else that the robot's going to have to do. And each of these states, including this state and this state, would have its associated transitions, triggers, and actions. Whew. So that is, kind of describing what this looks like, okay? We can also take it further, right, where we can have, if we describe this again, this is the initial state. We go into cleanup state. You can see here, if no trash is found, that's another option we could do, a cross hierarchy transition, where we can keep checking, and there might be another transition. So we have a recharge or no power transition, but what if we don't have any trash? We've looked around the entire complex, as an example. We haven't found trash, so we just go and park ourselves and get power, right, for some kind of time. So that way we conserve power instead of checking every single update, instead of patrolling the entire time, all the time. Don't patrol all the time. No trash was found in our initial test, and then in our initial thing, now go rest for a while. All right, as an example, when you're done resting, some kind of interval, and we can recharge at the same time. Maybe we spend some time, doing this kind of thing, and we haven't found any trash. And maybe we're even at half power. We don't need to charge anymore. We've gone through the entire complex. Go back and rest a bit, recharge, and when you're done recharging, rest some more. And when you're done, then start this whole cycle again. All right. So that's kind of something that you can do with our hierarchical, state machine. So there are some weaknesses to this too, and the challenges are, again, maintainability. But let's take a look at the problem. The problem is we'd like an implementation of a state machine system that supports hierarchical state machines. We'd like transitions that pass between different layers of the machine, right? Because you can see here there's different layers. Here's the outer layer, and here's the inner layer, right? This is the inner layer of the finite state machine. Okay, and the algorithm. Now this is the challenge when it comes to this. A lot of times we use something called recursive algorithms in order for us to do state machines. In fact, when it comes to any kind of behavior, and we're going to see this when it comes to learning, recursion is a thing that we do a lot in AI. Okay, we look at a method, and the method calls itself, and then if the method has been, when the method looks at itself, when that particular method has been satisfied, the base case has been satisfied, then it bubbles up to the next iteration, as an example, as opposed to using some kind of looping. Now, I got to tell you that looping is also possible. You can do standard iteration with while loops and for loops, but it becomes a little bit more difficult to write. That's all it is. It's not like it couldn't be written with a for loop or a while loop. It totally can be written, mostly while loops, by the way. But it's just a little bit more, I'm going to say, elegant when you see it in recursive format. Okay, so when it's recursive, you can say, okay, well, if I'm not done, then call myself back. Just to keep doing this until until I'm done, kind of thing. So recursion is something that's being used a lot. So again, the first part of the system is it returns the current state, and the result is some kind of list of states from the highest to lowest in the hierarchy. So again, highest would be the outer state. Either I'm cleaning up or I'm recharging. One of the two, right? And then there's something called the terminal state. If I'm in the terminal state, I've done all my cleaning up, or I don't have any more power, as an example, then it returns itself. This is part of this idea of a recursive state machine. And so you can have here's the outer state where you have state L and state M. That's the outer state, the outer level. And then you have some kind of inner states, state A, state B, and state C, which are inside of this state L. So state L itself would be the outer layer, and state A, B, and C would be part of the inner layer. Okay, whatever those states happen to be. Okay. So again, the second part of the hierarchical state machine is the update function. So what we want to do is we want to check every frame to see if we move, if we can transition from one state to the other. And here's an example with number transitions. So we have a transition that goes from state A to state B, and this is transition 1 as an example. We can then take transition 3 to go to state N outside of this state L, right? And then from here, the only place we can go is through state M back to state C, and maybe there's going to be some kind of, I think one thing that's missing here is a transition that takes us back to state A. So this could be a way of getting kind of full loop, or round trip, if you will, back to the initial state L. Okay? I know it looks difficult, but at the end of the day, what we want to do is provide some kind of transition that goes from an inner layer to an outer layer. Okay? And here's some example of the code. I'm not going to go into all the details here because we've already gone a lot more in detail than I'd like generally in a lecture, but for the most part, you would have some kind of hierarchical state machine base structure where you'd have some kind of update result, get actions and update, and get states. And then what you would have is a hierarchical state machine that inherits from or extends the hierarchical state machine base, and that allows you to recursively update the machine so that it kind of says, okay, am I in the right state? Take a look at my state. If not, go to the next state. So it's kind of interesting, more challenging to write, and it's many pages. I'm not going to go through this. This is for your viewing pleasure. Do I think that do I expect you guys to do a hierarchical state machine or an HSM? No, that's not really. It's kind of out of scope for what we're doing here in this course. However, you could do it. You can make simple ones that just that are not recursive and that are more hard coded. You can make a hard coded hierarchical state machine. There's nothing wrong with that, especially if, as an example, you have an outer state and an inner state, and you want to make sure that the character can transition easily from one state to the other. All right. So this defines hierarchical state machines. You can also combine state machines with decision trees. All right. So here's an example of that. I have an alert. Can I see the player? This is a tree, a decision tree. Yes. Okay, cool. Is the player nearby? Yes. Okay, go into the decision state machine, or the defend state machine. Okay, that's what happens. Is the player nearby? No. Well, I saw the player, but he's not nearby. Well, then raise the alarm. Go into that state machine, going through that functionality as well. Okay, and you can see that these alert, raise alarm, and defend are 3 different states that are inside of the decision tree. Okay, or they could be hierarchical states. Like I said, there could be a black box of other actions and transitions inside of these little states themselves. Okay, so decision trees and states and state machines can combine nicely. Here's an example of a state machine without tree transitions. So I have an alert, player is in sight, and player is far away. We'll then raise the alarm. Here's an alert, player is in sight, and player is close by. We'll then defend. Okay, so those different kinds of things you can do without the structure of a decision tree. And I'm not going to go through the rest, but that's mostly what I want to cover today, right, in terms of state machines. Nothing else. Any questions around state machines? And then I want to kind of go to you guys. What do you think? I'm kind of going to the chat here. We've talked about the 3 types of techniques now for making decision, and these are the 3 most common type of techniques that you're going to see out there outside of learning. Okay, so we're not talking about learning because most games don't do learning very well. But out of those 3 techniques, which ones do you have an opinion on? Which one would you do? Which one do you want to implement if you were going to make a game? Would you use a state machine? Would you use a decision tree? Would you use behavior tree? Which one do you guys prefer as an example? I'm not talking about for a specific context. Maxim just said, it really depends on the context, right? When it comes to, kind of quizzes, earlier before we started this, the lecture. So the context is, regardless of the context, you could write your AI however you want. And if you're going to choose a method that you want your AI or your AI for your games to follow, what would be the preferred method for you? So Maxim says state machine, especially with nested states. I agree. I think they're very straightforward. From a hard coding perspective, if you hard code your state machine, I think it's super simple. To kind of to create behavior for your AI. Super simple, right? Way simpler than decision trees. Decision trees require a much more complex data structure, right? They're quick. They're really fast. Compared to state machines, I would say they're even faster. They're more performant, right? But one of the challenges with a tree-like structure is it's predictable. State machines, you can make it so that there's more. It's not as I would say predictable, right? As a tree, and depending on how you write it, of course, right? So it's not as you can make it not as deterministic, a little easier, is what I'm saying, than in a tree. A tree is going to say yes or no. Do you go yes, left, or right? State machine is similar, but remember you can nest stuff one inside the other. In trees, it's hard to nest one tree inside of another tree. That would be kind of weird, right? Like you have a leaf, and that leaf is a whole other tree, and before you get to the next part of the tree in a decision tree, well, you have to finish what's happening over here. That's more challenging to write. Right, state machine's easier when it comes to that. Which level of state machines will we cover during the lab? So again, today we're going to be talking about your assignment mostly. That's what I want to try and do. I always try and do those things. But in terms of if we were going to hard code a state machine in lab, we would just do the basic finite state machine that's hard coded. That's what we would do. Making a state machine that is generic or general state machine, that can take some time to do. That means like you're making a game engine, not a game. And I think the general wisdom and consensus when you're making a small game, like how you guys are doing for assignment 3 and 4, or even for your game production course, make a game, not a game engine, I think is the wisdom. All right, I don't think it's a good idea to take your game and try and make it so that you can make any game from it. All right, that's not I don't think that would be the exercise. So in lab, then we would just do a hard-coded finite state machine. That would be a very basic one, not a hierarchical one. Okay. Any other questions or comments about state machines, decision trees, or behavior trees as we move into the next section? We're not going to do it this week, but next week we're going to talk about something totally different. Or actually, it's going to be a combination of. And then the following week, if I'm not wrong, and during week 12, we're going to be talking about learning. So, does anyone prefer, before we go, does anyone prefer something that's not a state machine? Like, would you prefer a behavior tree or a decision tree instead? See, to me, let me tell you my opinion. I think behavior trees are awesome. I think if you can pull off a behavior tree, the great thing about that is you have way more complexity. You have a sequence of events that go on. I want to select different kinds of behavior, based on, kind of what the autonomous character is seeing, right? And I have a whole sequence of events that I'll do different depending on my selector. I can also be random in terms of my selection, right? Whereas a finite state machine, you could put randomness in it, definitely, right? But just like a decision tree, the transitions and the decisions are going to be very basic, right? A behavior tree is way more complex, but what comes out of it is a more non-deterministic AI, right? So I like it from that perspective. Where it's difficult is maintainability and implementation. How do I implement a behavior tree? That's very challenging. And then we'll see as we get into learning, if we ever do the learning part, that behavior trees are, kind of one of the ways we're going to be doing learning. Okay, so that's it for me today. We've covered state machines. I'm going to stick around after we stop recording for a few minutes just to answer any kind of questions. Then we're going to head to lab again. Lab 1 is going to be starting at 12, and lab 2 is going to be at 3, and I'm going to be recording the one from 3 to 5. All right, so that's the one we're going to be doing today. Otherwise, guys, I'm going to stop recording this, and I'll see you guys during lab.